had to cut the other video short for a second. Not the ideal spot to end it, but my wife said she thought she found 2 ticks on the dog. So naturally, if your wife tells you that, you go inside and you take a look at the dog. There were no ticks, fortunately. Factor each of these completely. We'll go over the correct answers in a moment. Do all 4 of them. Oh, when I got interrupted before, hold on a second. Factor completely, it's code. It means 2 steps, maybe more, maybe a third, possibly. When I was growing up, if I heard Robert Carl Lindquist Jr., I knew that the beatings were about to begin. It was code for do it now or you're a dead man. So, like my mom, she'd say, clean your room. I really wouldn't listen too much to it. And then she'd say, I'm going to tell your father. And I still would be like, yeah. Then my dad would walk by and say, you got 5 seconds, Robert Carl Lindquist Jr., to clean this room or this crap's going out on the road and the garbage man's going to take it in the morning. What I do, I clean my room. Okay? So, factor completely is code, just like Robert Carl Lindquist Jr. was code. It means factor 2 steps, get it done. You have a complete job to do. It's not quick and easy. Go ahead. Do all 4. We'll go over them in a moment. Well, a moment, my time. Okay, so the first one, they share 3 in common. So I factor out that 3, and then I'm left with a trinomial that says x squared minus 3x minus 10. Well, that can also be factored into 3 times x minus 5 times x plus 2. You will recognize that as plan A, what we always try to do first. Okay? Now we go to the next one, and we look for a common factor. We see it. It's x. So I factor that out, and I get x times x squared minus 9. But hey, we just did a previous video which ended with the idea of the difference of 2 perfect squares. So we know that x squared minus 9 is x minus 3, x plus 3. So my full factoring here is x times x minus 3 times x plus 3. Remember, what students often do, in the first case is they forget the 3, and in the second case they forget the x. The reason is because it's not in a binomial, and they're so used to, when they see squared things using binomials, you have to put down anything that you factored out as part of the answer. Okay, try the third one. That shares a 3 in common, or I should say an x in common. So I factor out the x, I get x squared minus 25. That becomes x minus 5, x plus 5, in either order, of course. Make sure you use all 3 factors, x, x minus 5, and x plus 5. Why that disappeared, I do not know. And now the last one, x to the 4th minus 16. Think difference of 2 perfect squares, but this is a new style of factoring. But apply the same logic you've been applying. Well, you've already tried it, so let's go with it here. Ready? X squared plus 4, x squared minus 4. But that x squared minus 4 is also the difference of 2 perfect squares. That can become x plus 2, x minus 2. So altogether, I get x squared plus 4, x plus 2, x minus 2 as all of my factors. So key ideas to take away from this slide. A little reinforcement of difference of 2 perfect squares. Plan A is an example of factoring completely. We have the special case there of where you have difference of 2 perfect squares, but then they actually wind up being squares, and then you can factor a second step. And then factoring completely. Okay, that was that phrase. Now a little review of the quadratic formula. Here are 2 questions to try. Try the one on the left, then we'll try the one on the right. Okay, assuming you've done your stop and start. The one on the left, A is 1, B is 4, C is negative 19. So, according to my quadratic formula over here, the negative of b is negative 4 plus or minus the square root of b squared, which is 4 squared, minus 4 times 1 times negative 19, all over 2 times 1, which is 2. So x will equal negative 4 plus or minus the square root of 16 plus 76, which adds up to 92. Of course, it's over 2. And the square, now if I said to leave this answer in radical form, I'm done. And most often it is in radical form, but sometimes they want you to go through to a decimal. Square root of 92 is about 9.6 rounded off. That gives me 5.6 over 2. If you do negative 4 plus 9.6, you get 5.6. Negative 4 minus 9.6 is negative 13.6. Dividing each by 2, I get 2.8 and negative 6.8. Okay? All right, you try the next one. Remember, before you begin, get it all on one side. Okay, I'm assuming you did stop and start. So this becomes, I didn't do anything with the top. This is from the previous slide. I apologize about that. If we get this all on one side, we get 5x squared minus 11x minus 104 equals 0. Oh, I don't know why I have 104 and why I have 15 here. Let's go with the 15 that I have worked out. I don't know why this discrepancy exists, but let's just go with the 15 and follow the steps. The negative of b, which is negative 11, which is 11, square root of negative 11 squared minus 4 times 5 times, as I have it up here, negative 15, over 2 times 1, which gives me 11 plus or minus the square root of 121 plus 300 over 2, which is 11 plus or minus, add those up, square root of 421 over 2. Now, if I asked for simple radical form, well, we're not going to talk about simple radical form in here because we didn't teach and we won't teach simplifying radicals. But we'll just get radical form, which is radical 421 over 11 plus or minus 20.5 over 2, because if you do the square root of 421, it's about 20.5. That's 11 plus 20.5 is 31.5 over 2, and 11 minus 20.5 is negative 9.5 over 2. 31.5 over 2 is 15.8. Negative 9.5 over 2 is negative 4.8. Round it to the nearest tenth. Okay, so now we have this problem that says which quadratic equation has roots 2 minus radical 3 and 2 plus radical 3. So we've talked about test savvy a little bit in class, and we'll do it on this one. I started with 4 circles on the 4 choices because for now, let's assume it can be any of the choices. There's the quadratic formula in front of you. Now you really have 2 choices. You can do the quadratic formula to every single one of these choices and hope that you get to the point where you find the correct solution. That's a lot of work. Or you could analyze how each of these choices would be affected by the quadratic formula and how it would relate to the roots it's supposed to get, the answers, that's all root means, of 2 minus 3 and 2 plus radical 3. So I'm going to give you some time to ponder it. When you've thought about it as much as you can, start the video up, and then I'll go through elimination. Okay, so you have now decided to check it out. Let's see if you got it right. First, I want you to note that this is a positive 2 in the answer. So when this says negative b, see this minus radical 3 plus radical 3, that's the radical stuff here. That 2 is in the place of the negative b. So, and we're going to divide out later. But the big thing I want you to notice is it's positive. I'm not worried about the value of 2, it's positive. So, to get this to be positive, and the formula says the negative of b, b itself has to be negative. So, that means that we can ditch choices 2 and 4. Now we're looking at 1 and 3. Which one would work? Well, now I'm only worried about the part that says b squared minus 4ac. In fact, that actually has a really fancy name called the discriminant. We're not going to do much with that right now, but it is important because it'll tell you a little bit about the roots. I want to come as quick as I can to a radical 3, as close as I can, because this whole divided by 2 thing is something we don't do a lot with. But if I do choice 1, which says negative 4 squared minus 4 times 1 times 7, substituting the values in, I'm going to get 16 minus 28, which is negative 12. If you take your calculator and you type in the square root of negative 12, you're going to get error, error, error. That's actually an imaginary number. And we don't have imaginary numbers here. We have real numbers. So I don't think that's the answer. But let's go with what the other one says. Negative 4 squared minus 4 times 1 times 1, which is 16 minus 4, which is 12. Now, the truth of the matter is that if I was to simplify radical 12, I said we don't do any simplifying radicals in this course, but if I did, I would come out with 2 radical 3, and then that 2 would cancel with the 2 in the bottom. Bottom line is, because the first one is a negative under a radical and the second one is a positive, you at least know that you can get choice 3 out of the deal, because negatives under radicals are imaginary numbers. this answer can be simplified because the radical 12 is actually 2 radical 3. If you understand that, that's great. If you don't understand it, it's, you know what, there's 16 lessons in the course. I should say 32 lessons in the course. 3 of them are tests, 3 of them are pre-tests. So that becomes 26 lessons in the course, and there's only so much that we can study. And I always want to make sure I spend, you know, the first quarter to third of the year reviewing a lot of high school stuff and making sure the fundamentals are sound before we start taking off, which we have been the last couple of weeks and will continue to do today. And speaking of taking off, we might not have the time to delve into how to simplify radicals as a topic in the course, but we certainly have talked about the Pythagorean theorem, leg squared plus leg squared is hypotenuse squared. And here is an opportunity, more code here. See how it says to the nearest hundredth of a meter? That means you're going to need the quadratic formula. So start with leg squared plus leg squared is hypotenuse squared, and then we will get into the quadratic formula. Okay, so leg squared plus leg squared is hypotenuse squared. The first leg is x, the next leg is x plus 1, and the hypotenuse is 6. So let's just do a little algebra here. That's x squared plus, now x plus 1 squared means x plus 1 times x plus 1. That's going to equal 6 squared. So all I'm doing is a little bit of work here in this middle bracket. Double distributing, I get x squared plus x plus 1. And then simplifying, 1x squared and another x squared is 2x squared. X and x make 2, plus 1 is 36. Subtracting 36 from both sides, and I get this quadratic equation that says 2x squared plus 2x minus 35 equals 0. Now, I might, in fact, but I would try to factor this a bunch of ways to Sunday to get it down pat. But when I see this phrase, nearest hundredth of a meter, that means decimals, and decimals come from the quadratic formula. So I'm going to go with the quadratic formula, which I have highlighted here. A is 2, B is 2, C is negative 35. Plugging the numbers in here, I get negative 2 plus or minus the square root of 284 over 4, which is negative 2 plus 16.852. Now, I made sure I went out at least 3 decimal places because they want the nearest hundredth. So if you go out an extra decimal place, which is 3 places, when I round off, I'll be accurate. If you only go to 2 places, you may or may not be accurate. Now, negative 2 plus 16.852 is 14.852. Ooh, it should be over 4. I made it over 2. That's a mistake. Oh, boy. Let me tell you verbally what that is. I changed it to a 2. That's a mistake on my part. Sorry about that. 14.852 divided by 4, not 2, is 3.713. Okay, so that's 3.71. Again, 3.71 is one possible answer. For the other one, it would be negative 2 minus 16.852. But you know what? I don't need to check that answer because that would give me a negative. And I can't have a negative length, so I don't need to do that one. I just need to do the plus one. So again, that should be 3.71, and then that is this leg over here, 3.71, and the other leg is that plus one, which is 4.71. So 3.71 and 4.71. Again, I made the mistake here. This should be a 4, not a 2. And that makes this 3.71 and the other one 4.71. All right. Now, this is a little tough to see, sorry, but it says quadratic equations. It looks a lot better on my screen. Solve for x. X squared minus 11x equals 26, and 3x squared minus 7x plus 6 is equal to 0. Okay, so that first one says x squared minus 11x equals 26, and the second one says 3x squared minus 7x plus 6 is equal to 0. Factor each, solve. Go ahead. Okay, we've had time for stop and start. So In the first one, I factor to, or it says x squared minus 11, x minus 26 equals 0, getting everything on one side. I factor to x minus 13 and x plus 2. Maybe it's the guy on the left, maybe it's the guy on the right. Adding the 13, subtracting the 2. X is 13 and x is negative 2. It's quadratic, second power, 2 answers. Next one, getting it all on one side. Or I should say it is already on one side. Now there's no common factor, so I go to plan B, multiplying that 3 by the 6, and I get x squared minus 7x plus 18. That's x minus 9x plus 2. Divide back in by the 3. Gives me x minus 3 and 3x plus 2. Solving each, I get 3 and negative 2/3. Okay? So those are my correct answers. If you can do those two, you're excellent at quadratic equations. Okay, so that's kind of everything that we've been doing in review, and it's time to go into functions. And functions are really important because they explain phenomena around us, the world around us. There used to be a TV show years ago called Numbers, and it was about a mathematician that would use logic and reasoning to solve crimes. And what you see with this is this ability when you perceive the world through functions, which is what the guy in that show, his name was Charlie, did. It allowed you to get correct answers to situations because of the way you think. And that's what functions did for me. They taught me how to think. It explains things like flight. It explains how the grass grows. It explains how the eye see. It explains the DNA inside this bird that makes it, say, a pelican and not a snowy owl. Okay? It explains the weather patterns that bring the snowy owl, who lives up north, south during the winter. It explains the parabolic bend in this fly rod of my buddy Eric on the Salmon River. It explains the bend in my fly rod and the trajectory of this fly line when I was up in Labrador a few years ago. What is a mathematical function? A mathematical function is a rule or a law that defines a relationship between one variable, the independent or input variable, and another variable, the dependent or output variable. So basically, a function is a relationship between input and output. It's a relationship between input and output, and that relationship defines, because it's a rule, what happens to the input that turns it into the output. Examples are, for instance, 16x squared minus 90x plus 15 is equal to y. That particular one, if I made it a negative 16x squared, would have a lot to do with gravity. F of x equals 9x squared minus 90x. Or y equals 4 times x plus 3 minus 7. All of those are functions, and all of them can be readily understood in terms of a function box or a function machine, where there's certain inputs and they correspond to certain outputs. The function changes the input into a brand new output. Might be equal to it, but it might not be. Now, there are 4 ways to express a function. One way is with a function box. Another way is with a graph. The third way is with a diagram. And the fourth way is by giving you the function rule. All 4 of those are really good pictures of understandings of a function. Okay? So I'm going to start by going over a picture of it, like we have on the right-hand side here. So we start with the numbers 1, 2, 3, 4, 5, 6, and 7, and we're going to call this function f of x. So f is going to transform, kind of like the movie Transformers, you know, with, I think it was Shia LaBeouf and Megan Fox, and I don't even know the names of all of the Transformers, but one minute they might look like a car, and the next minute some kind of an invincible robot. Well, this particular function, f of x, changes a 1 into a 1, a 2 into a 3 into a 5, 4 into 7, 5 into 9, 6 into 11, 7 is to 13. Anybody think of what this function might be? Yeah, if I did it as a function rule, it would be f of x or y, it's the same thing, equals 2x minus 1. Multiply the input by 2, subtract 1, and that gives you your output. So, according to the rules, this function that I drew for you, let's find these values. What is f of 1? when I write it that way and I say f of 1, that means the input is 1. What's the output? It's 1. What about f of 2? Well, the input output, you could see it in the arrow there. It goes from the left to the right. If you input a 2, you output a 3. What if you input a 3? Then you're going to output a 5. What if you input a 7? Now we're jumping up here. Inputting a 7, we're going to output a 13. Okay? All right. Now, here are some questions to answer. And this is all to get you familiar with vocabulary. We're going to do a slide just like this in a minute, except I'm going to change the numbers. What is the image of 4? That means if the input is 4, what's the output? That is 7. See if you got to wait. What's the image of 5? If the input's 5, what's the output? According to the diagram, 9. Now, pre-image means go backwards. It means start on the right side and go back to the left side. What's the pre-image of 3? In other words, 3 is now an image. What did you start with to get the 3? That's 2, right? Here's the 3. The pre-image is 2. So images go left to right. Pre-images go right to left. What's the output if the input is 6? So there's the input of 6. The output is 11. All we're doing is getting comfortable with terminology here. The next thing is a little bit of a definition idea. Domain means the set of all of your input values. So all of my input is all of the numbers in the left-hand oval here. So it is 1, 2, 3, 4, 5, 6, and 7. What's the range? Well, those are all the output values, and those are on the right. So that would be 1, 3, 5, 7, 9, 11, and 13. Okay. Now, here's another function. Answer those questions. Okay. F of 1 is 11. Why does that say 1? Should say 11. 1 turns into 11. What about f of 2? 31. The function is taking an input and it's transforming it into an output. What of f of 3? 51. What about f of 7? What does it turn into according to the function? 131. Okay? Now let's try these questions. Okay, what's the image of 4? 71, right? 4 turns into a 71. What's the image of 5? 91. What's the image of 6? Oh, I'm sorry, that's not what it says. It says, what is the pre-image of 91? Well, the pre-image, if you start with 91, goes backwards, you get 5. What's the output if the input is 6? 6, output 111. List the domain of f. It's the same as before. 1, 2, 3, 4, 5, 6, 7. What's the range of f of x? Range is output. The output would be 11, 31, 51, 71, 91, 111, and 131. Okay? So that's a good picture of the relationship, and you're growing more comfortable with the terminology. Okay. Now, notice this one at the top. It doesn't say f of x, it says f inverse of x. And inverse functions go backwards. You switch the domain and the range. Whereas x usually indicates a domain element, y usually indicates a range or output element. X input, y output. Okay. Notice I changed these all to f inverse of x. F inverse, f inverse, f inverse. Go ahead, find these values. Okay, f inverse of 1 is 1, right? F inverse goes backwards. Start with a 1, end with a 1. What about f inverse of 5? That would be 3. Start with 5, go backwards to 3. What about f inverse of 2? There is none. there's no 2 on the right-hand side to go backwards and find what you started with. So we call it the empty set. Set symbol, squiggle on the left, squiggle on the right, nothing inside. What about f inverse of 7? There's my 7. What I had to go back to is a 4. Okay. Now remember, this is the inverse function. So with the inverse, we go right to left. So make sure you look at those things when you answer this. Okay, I assume your stop and start is done. What's the image of 4? There is none, right? There's no 4 on the right-hand side. What's the image of 5? It's 3. What's the pre-image of 3? Now we go over here and go backwards. That would be 5. What's the output if the input is 9? Remember, we're switching sides here for inverse functions. Input 9, output 5. List the domain of f of x. The domain of an inverse function is everything on the right-hand side. 1, 3, 5, 7, 9, 11, 13. What's the range? Left-hand side. So the range is what comes out of things. The domain is what goes into things. So you can see that all of these arrows have reversed from the previous slide because now the arrows are pointing to the left. So it reverses image and pre-image. It reverses input and output. It reverses domain and range. Now, picturing it and getting used to the terminology is one set of things, but most of the time we just tend to write a function rule and ask you to use the rule to evaluate. For example, if I wanted to find f of 3, this means that 3 is my input into this function machine. So if my input is a 3, this says f of the input is 3 times the input minus 5. So this means 3 times 3, because my input is 3, right? X stands for input. Here's my input, 3 times the input minus 5. In this case, it's saying, hey, let's use 3 as an input. 3 times 3 is 9, minus 5 is 4. Okay, you try the next one, f of 5. Okay, so the input is 5. 3 times 5, which is 15, minus 5 is 10, not 11. Sloppy mistake here. So 3 times 5 is 15, minus 5 is 10. Ding, ding, ding. Daily dumb mistake. That's 10. Okay, run out the next 4 in that left-hand table. Okay, so if I input a 10, 3 times 10 is going to be 30, minus 5 is 25. If I input a negative 4, 3 times negative 4 is negative 12, minus 5 is negative 17. Right, that makes sense, because if I'm at 12 negatives and I go down 5, I ought to get I ought to be lower than negative 12. Negative 17 indeed is. Next up, 3 times negative 7 is negative 21, minus 5 is negative 26. And 3 times 12 is 36, minus 5 is 31. Okay, so now let's have you evaluate each of the following in this function, but I want to be careful about something. Remember the order of operations, PEMDAS? I think we mentioned it on the first day. 2 times x squared. What do you do first? Do you multiply by 2 first, or do you square first? Yeah, you definitely square first. So this, if read properly, says g takes the input, it squares the input, then multiplies by 2, then subtracts 1. So that's the best way to understand this, is you take the input, you square it, then you double that result, then you subtract 1. Try the first one. Okay, so this is 2 times 3 squared minus 1, because 3 is my input. 3 squared is 9. Do that right away. Then 2 times 9 is 18, minus 1 is 17. Try g of 5. Okay, so that would become 2 times 5 squared minus 1. Square that 5 right away, because that gets done by order of operations. 5 squared is 25. 2 times 25 is 50. 50 minus 1 is 49. Okay, now you try the next 4. Go ahead. Two times 10 squared is 2 times 100, which is minus 1, of course, gets you 200 minus 1, which is 199. input of -4. I got to square that -4. That gets me to 16. 2 times the input. 2 times 16 is 32. Minus 1 is 31. This time a -7. 2 times -7 squared minus 1. -7 squared is 49. 2 times 49 is 98. Minus 1 is 97. And last but not least, g of 12. The input is 12, so it's 2 times 12 squared minus 1. 12 squared is 144. 2 times 144 is 288. Minus 1 is 287. Okay. Last thing I want to do is talk to you about types of functions. Now, there's 4 types I want to discuss today: linear, quadratic, cubic, and absolute value. And this is just to be able to recognize the functions. Tomorrow I'm going to add exponential to the list. Or at least in the next couple of days I will. An example of a linear function. Linear just means the highest exponent on the input is 1. So y equals 3x minus 1, y equals -2/3 x plus 1. In other words, y equals mx plus b is a linear function. These make straight line graphs. And the first 4 letters of linear spell line. Very good. Quadratics we just talked about. We just did a unit on them. We're solving quadratic equations. Quadratics have things squared. The highest exponent is squared. So, examples: y equals x squared minus 7x plus 1, y equals 3x squared minus x. Quadratic, you recognize it by the exponent is squared. Linear, you recognize by the highest exponent is 1. Cubic, the highest exponent is 3. So, -0.5x cubed, or 2x cubed plus 4x squared. And last is this thing called absolute value, which I'm sure you've seen. I remember seeing it for the first time in 7th grade with Mr. Muller, who caught me cheating on a quiz, but that's a long story. Absolute value symbols are these bars. So h of x equals 5x minus 4. Okay, absolute value 5x minus 4, or 3 times the absolute value of x plus 7. So those are function rule examples, but graphs are also there. A linear graph looks like a straight line, like that. Quadratic graph looks like a parabola, either right side up or upside down. A hold water parabola, as Mr. Braze would say, or a leak water parabola. Notice that the equations are squared. You get the parabolic shape for quadratic. And for linear, it's y equals mx plus b. Highest exponent is 1. Cubic. There's an example of a cubic. Highest exponent is 3. I don't care if it's just the 3 or if it's 3 and then the squared and then the 1 and then the number. Bottom line is, it kind of looks like a parabola that didn't flip right back the way it normally would. An absolute value is a b. Parabola is a gentle curve. Look at the quadratic example. The parabola is a gentle curve. Absolute value, sharp, hard turn with the v. Okay, so we've begun our study with functions. We worked it out a little bit. We will continue to work on functions in the coming lessons. Okay, happy recap. Define each of the following. What's a function? It's a relationship between input and output. It's a rule that it follows. Domain, set of all the inputs. Range, set of all the outputs. Linear, forms a straight line. Highest exponent is 1. Quadratic, highest exponent is 2. Forms a gentle U shape that we call a parabola.